Hey everyone, I'm Ting founder of Chain of Thought Research, where we uncover the most important trends in AI. And welcome back to our 10-minute research briefs. So the other week I was thinking, what if an AI driving your car made a mistake? Not just a wrong turn, but a real mistake. Or what if an AI trading bot managing millions of dollars secretly deviated from its strategy, putting everything at risk? We are putting more and more trust in AI to make critical decisions for us. Decisions about our health, our finances, our infrastructure, and every time we use one of these powerful AI models, we are essentially relying on a promise. The company behind it promises they're using the model they advertise. They promise the result hasn't been tampered with. But here's the problem. Most AI today is a complete black box. We can't check, we can't prove what ran, how it ran, or if the answer is legitimate. We just have to trust them. But what if we didn't have to? What if we could replace that trust with mathematical proof? This is the goal of a new and incredibly important field called Verifiable AI. It's a race to build the accountability layer for the age of AI. And the builders in this race are facing a fundamental challenge, something we call the verification trilemma. And to understand this trilemma is the key to understanding how we can make AI something we don't just have to trust, but something we can actually verify. So what is this trilemma? Imagine a triangle. Every team building a verifiable AI system has to pick a corner. They can optimize for cryptographic purity, practical speed, or economic scale. But here's the catch. Right now, you can't have all three. Every solution is a trade-off. Let's start with the ideal, cryptographic purity. This approach is what we call zero-knowledge machine learning, or ZKML. Think of it as a magic receipt. Let's say an AI analyzes your private medical data. ZKML can generate a cryptographic proof, our magic receipt that proves the AI ran correctly to produce its diagnosis. But it does so without revealing your private health information or the hospital's proprietary AI model. Just math. You don't need any trust. So this is the gold standard. But here's the problem. Generating that proof is incredibly slow and expensive. We are talking about 1,000 to 10,000 times the cost of just running the AI inference in the first place. A single response from a large language model could take days to prove. But builders are racing to make this practical. We have teams like Lagrange Labs that are creating new proof systems like Deep Proof, which they claim can be up to 185 times faster than previous methods. And then we have hardware companies like CISIC and Fabric, which are building custom computer chips called ASICs, designed to do one thing and one thing only: generate these proofs at lightning speed. So that's one corner of our trilemma. Pure, perfect, mathematical proof that's still a little bit too slow for most things today. So what if you need an answer right now? That brings us to the second corner, practical speed, using something called Trusted Execution Environments, or TEEs. In a TEE, code and data go in, they're processed in total isolation, shielded from the operating system, the cloud provider, or even the owner of the machine. And when the computation is done, the vault produces a signed message called an attestation. This is a digital signature that says, I swear this specific code ran on this specific data and produces this exact result. And the best part, it's really fast. The performance overhead can be less than 2%, even for massive models running on GPUs like NVIDIA's H100 in their new Blackwell architecture. This is not a futuristic dream. It's already being used in production today by companies like Fala Network and Itoma. But there's a catch, and it's right there in the name: Trusted Execution Environment. You are placing all your faith in the integrity of the chip itself. You have to trust Intel, AMD, or NVIDIA not to have a bug in their hardware. And history shows us that trust can be broken. Hardware flaws have happened before, and they bring the entire security model down. So TEEs are the fastest path today, but for some, that single point of trust is still a little bit too much to ask. Okay, so we have the pure but slow path, and then we have the fast but trusted path. This leaves the third corner of our trilemma, economic scale. So to me, this is a bit of a wild card. And it's often known as optimistic machine learning, or OPML, as one of the key parts of this. And in this way, an AI posts a result of its computation. It puts out a financial stake, like a security deposit, and it's assumed to be correct or optimistically valid until someone challenges it within the set time window. If someone spots an error, they can start a dispute. If the original result was wrong, the challenger wins and the cheater loses their deposit. So the beauty of this is speed and cost. You don't pay for a complex proof every time you do a computation. Verification is only done when someone cries foul. The trade-off here is stability. The whole system depends on having at least one honest person watching. If the reward for challenging is too low, or if no one is paying attention, bad results can slip through. So for now, I would say OPML is more of a fascinating experiment. It's a clever idea, but not ready to anchor trust for real-time critical AI systems. So that's the trilemma. A choice between the mathematical purity of ZKML, the pragmatic speed of TEEs, and the economic, interesting design of OPML. No single solution is perfect yet. And this is a big but. Solving this is a really, really big deal. In fact, some analysts estimate that the market for verifiable AI could be worth over $100 billion a year by 2030. That's in line with our own internal research. This is not just a niche idea. It's going to become the foundation for the future of trusted AI. So let's imagine for a second that these builders succeed. What kind of world does verifiable AI actually unlock? This is where it gets really cool. First, we'll have AI oracles that can actually reason. Today's crypto oracles give us simple facts like the price of Ethereum. Verifiable AI allows an oracle to provide a trusted judgment. A smart contract could cast an AI. Is this loan application too risky based on this person's financial history? And get back a verifiable answer. It turns AI from a simple data provider into a trusted decision maker. And second, we can get autonomous AI agents with enforceable guardrails. The next generation of AI is going to be autonomous AI agents managing our work, treasuries, executing trades, making decisions for entire organizations. That's an incredible amount of power, and it needs limits. Verifiability can turn those limits into unbreakable rules. You could program an agent that is mathematically incapable of violating its approved risk parameters, because every single action it takes would require a proof of compliance. And third, all of this leads to decentralized marketplaces for AI models. If you can prove which model ran and that the output is legitimate, you can start treating AI models as verifiable assets. Users could pay per inference for access to a model, confident that they are getting what they are paid for, while the model's creator can protect their intellectual property. So the future is incredibly exciting, but there are huge challenges ahead. For one, verifiability has to be invisible to developers. It needs to be simple as adding a single line of code like verify equals to true to their existing workflow. And of course, the economics of all of this has to work. Verification is not free. Networks need to be designed with the right incentives to pay people to run the complex hardware that generates and checks all of these proofs. And there's an even bigger, more important challenge out there, and it's something that we need to understand. Verifiability is not the same as ethics or being correct. A cryptographic proof that an AI did something wrong is still a proof. A model can be biased, it can be harmful, it can be manipulative, and still generate a perfect verifiable result. Verification proves that the computation was done correctly, but it does not say anything about the outcome, whether it was right, whether it was fair. So proving what a model did is the first step. The next, much harder step is building systems that can verify its behavior over time and align its reasoning with our value. For decades, we've learned to interact with technology based on trust. We trust that the app is secure. We trust that the server is honest. We trust that the outputs we get are real. But as AI agents begin to move money, allocate resources, and shape our world, the cost of blind trust is becoming too high. The stack for verifiable AI is still early, but the direction is clear. Just as HTTPS made secure communication the default for the internet, verifiable inference could make machine decisions accountable by default. We are finally starting to build the tools to open the black box, to create an AI layer that can prove its steps, explain its reasoning, and stand up to scrutiny. We are building the foundation layer for accountability in the age of AI, and we need to get it 100% right. Okay, I know that was a lot. My job is to read all of these dense reports on this stuff so you don't have to. If you want more research briefs like this one that go deep on the future of AI, consider subscribing to our channel. And thanks a lot for hanging out. See you in the next one.